Again, welcome to Data Structure and Algorithm. This is CS435 course given at Rutgers University. So in these lectures, we will go through the concept of trace data structure. So we're going to learn about binary trees, and also we're going to explore various binary tree transversal algorithms. So first, we will start with the definition of trees and also some few terminologies that we use in trace data structure. So a tree is a nonlinear data structure in which the elements are organized into an hierarchy form. So we went through linear data structures already, such as stacks, queue, and linked lists. And there we can see that each item is placed either in a stack, queue, or linked list in sequential order, one after the other. This is opposite of trace. In trace, data are organized in the form of hierarchy. So we may have a node. So here we see a trace comprises of a set of nodes in which elements are stored. So the node is where the elements are stored. And the edges will connect to another node. So normally in a tree, we may have a node. And instead of having a node in sequential order, such as linked list, one node may have a children. So it will be from up, down. So it will be in the form of hierarchy. And again, we're going to use the diagram to explain the concept here. First, let's go through the definitions and also most terminologies we use. So here we say each node is located on a particular level. And also there's only one root node in the tree. Also, nodes at the lower level of a tree are the children of nodes at the previous tree of the previous level. Also, a node can have only one parent, but may have many children. Also, nodes that have the same parents, that means they will be on the same level, are called siblings. Also, the root is the only node which has no parent, because that's the starting of the tree. Also, a node that has no children, we use the term a leaf node. So a leaf node have no children. That will be the node at the bottom of the tree. Also, a node that is not the root, and also at least it has one child, is called an internal node. It's not a leaf node because it has a child. As we said, a leaf node has no children. Also, a subtree may be part of a tree of the whole tree. So here we say a subtree is a tree structure that makes up part of another tree. Also, we can follow a path through a tree from parent to a child, starting at the root. And also a node is an ancestor of another node if it is above it on the path from the node. Or we may also use the term descendants if it's below through the path. So now let's use the diagram to explain the whole concept of trees here. So here we can see that our items are arranged in hierarchy form from up down, not in sequential order. So that's why we said in the definition, a tree is a non-linear data structure. Again, data structure is how data is organized in a program or in application. So we have node A. That will be our root because that's the beginning of the tree. So for example, anytime if we write a code and we want to know if the tree is empty, there's nothing, we just need to check if the root of the tree is pointing to no, or I would say it's equal to no, then that means we don't have no. So a tree must have at least a root. The first node that comes in, this will be the root. So the next we have node B, C, D, E. These trees, these nodes are the children of the root because they are below the node A. And we may call this also level 1 or the level, first level. then we can see that node B is called internal node. Why? Because you have children and also you have parents, at least one child. In this case, it's two. Then we can say node F is what we call the leaf node. It has no children. And also LM, NO, P, and K, they are all called leaf nodes because they have no children. Also node C is a leaf node. D, E, I, J, H, they are all internal nodes. So here we say the nodes that can be reached, any node can be reached by following a path from a particular node, are called the descendants of that node. So for example, I can reach from A to N and my path can be A, D, then when I go D, I'm not going to go H because if I go H, H is a leaf. Actually, previously I mentioned it's internal node at the end. So we can see again, H doesn't have no children, so it's a leaf. So I can have from ADH, I will end up at H because it's a leaf. Now, if I want to reach N, I have a couple of options. I can go, the path can be A, D, then I, then N. So again, the level of a node is the length of the path from the root to the node. Okay, the level of a node is the length of the path from the root to the node. And also the path length is the number of edges followed to get from the root to the node. And the height of a tree is the length of the longest path from the root to the leaf. So let's see here, what is the height? We can see the longest leaf is LM, NOP. They are all in the same level. So the height of the tree will be from the root to any of the leaves, NOP, LM. Now we can see the first BCD is in level 1, the root is level 0, then FG, H, I, J, K, they are in level 2, then LM, NOP, I in level 3. So to find the height of a tree, we can say is the number of levels plus 1, because we start from 0. So that's the concept here. We can see the root is level 0, then BC is level 1, DE level 2, FG level 3. So the height of this tree will be 4. Now we can classify trees based on the number of children they have. So here we say trees can be classified in many ways, but one of the most important criteria, which is what we are going to cover in this lecture, is based on the maximum number of children any node can have. That's why we use the term binary tree. Our lectures cover binary tree. Binary tree is one of the simple tree concepts and data structure because the children cannot be more than 2. By means 2. So in this case, it's kind of more straightforward to implement it. But we can imagine if we have trees and we didn't specify the number of children, if we are going to implement it, it may be a little bit difficult because, again, in our data structures, and let's say the node, how many possible leaves how many possible children we are going to consider. In this binary, we can say left child and right child, and those are the 2 main instant variable we are going to use. But if it's 5 children, then we have to use 5 instant variables, 1 to represent the possible children because the node can have up to 5. So here we say again, one of the important criteria is the maximum number of children in a node in the tree we have. This may again refer to as the order of the tree. Now, general trees have no limit to the number of children a node may have. And a tree that have a limit, we may normally call it the tree name by the number of children, such as binary trays means by 2. So example here, n children is referred to as n-ary tray. So if it's 3 children, we call it trinary or trinary tray. So again, there are few definitions here. What is a balanced trace? Yes, we say a trace in which the node may have at most 2 children are called a binary trace. Again, the key word is at most. So each node may have 0, 1, or 2 children, not more than 2. And that's what we are going to focus, the type of trace where we are going to focus in these lectures. Now, a trace is balanced if all of the leaves, that's all of the leaves of the tree are on the same level or within one level of each other. So the example of the diagram here, you can see on our left side, this is called a balanced tree, because we can see the leaves. Again, a tree is balanced if all of the leaves of the tree are on the same level or within one level of each other, not more than one level. So this is a balance. We can see one leaf here is one level above, which is okay. But the second diagram is unbalanced because we have a leaf, one above is okay, but 2 above. It's not a balanced tree. So a balanced tree normally have leaves on the same level or one above. So as we said, we focus on binary trees. So here we say a binary tree T is either empty or it has a special node called the root. So when a binary tree is, or if any tree is empty, the root may point to no, there's nothing. So our option here is that a binary tree can have a special node called the root node. Also, the tree has 2 sets of nodes since you have 2 children. The LT will stand for the left child or the left node, and then the RT will stand for the right child or the right node. So we call this again the left subtree and the right subtree. So the left and the right are also binary trees. Again, we will see the concept in the diagram in a few seconds. So a binary tree can be shown as following. So we can see the root is A, it has the most 2 children, BC. So I can call B as a left child of A, or I may call it a left subtree because it goes down left subtree. So we can also see node B have 2 children, D and E, but node D have only 1 child, G. And G is a leaf because it doesn't have no children. E also is a leaf, no children. Same thing applied to F, have 1 child, H, and H have no children. And this small example of a diagram. So all this again, they are all binary tree because when we look at each, either the node have no child or 1 child, and the most not more than 2. So node A have only 1 child, node B have only 1 child, and node B is a leaf. And the second diagram, node A have 1 child, node E also have 1 child, and node B have 1 child, and node E is a leaf, and etc. So again, the binary tree can have at most 2 children. So as we said, we focus on implementation of binary tree here. So we are going to start with the classes. So since a binary tree consists of, in this case, we are using node, the node implementation, which is dynamic implementation. We can also use array. We may look the concept of array implementation of binary tree later on. So here we start with the linked list implementation. So which means we need nodes. So we may have a class called binary tree node. This concept is the same as when we did the stack implementation. When we do the stack array implementation, in the stack class, again, we declare our array, we specify the size, and we use it from there. But when we are doing the linked list or the stack implementation using the linked list, which is dynamic implementation, first of all, since we know that dynamic implementation using a linked list, the linked list consists of node. So we had a node class, which will be used by the stack. The same thing here. We are doing the linked list implementation of binary trees. So we're going to have the node class. Here we are calling it binary tree node. And then these nodes, that's what we'll be using to create our tree, our binary tree. So if we have a binary tree node, the instant possible variables again will be the info. The info is where we have one node, like linked list. When we do a simple linked list, one node have two parts, the info part and the address of the next node that is pointing to. Then when we do the double linked list, we have three parts, the info part, an address that is pointing to the previous node, and also address pointed to the next node. Here we have a binary tree node. It has the info part where we are going to store the data. Then there's a possible that this tree may have the maximum two children. So we have the left link, which will be pointing to the left child of the node. Then we have our link, which will be the pointing to the right side, the right child. So here we say info stores the information part of the node, and L link or left link point to the root node of the left subtree. And then the right link or R link point to the root node of the right subtree. So this is our class. We have our instant variable info. The data type is T, again, that's the generics. Then we have the left link and also we have the right link. We can see it's the same as the linked list implementation. The left link and right link, the data type will be the name of the class. This is address pointed to the next node, left and right subtree. So the data type will be the class type, binary tree node, binary tree node. Then we have our constructor for the binary tree node, default constructor, which is called the binary tree node with no argument. Then we have our constructor with parameters, binary tree node, we have T. So T will be our data type for the info part. Then the binary tree node for the left and binary tree node, those are all the data type. So it will be the left subtree, the right subtree, and the info. So we can specify or set those. So next we have the cron method, and here is to cron our node if we need one. And also as usual, we have the string method, which will be when we want to print or represent our info in a string form, we will call this formatting. Now we can see the inheritance concept here. So again, we may have our main binary tree class must inherit the binary tree node. It's going to use the binary tree, the node, to create the binary tree. So next we'll go through the binary tree class also. So this is the concept again. We have the root node. The root is the only node that have no children, and it's called A. So this is more or less like our pointer. When we are doing linked list, we have pointer P, and we say pointer P point to no, it means the linked list is empty. The same concept here. Here we have a special node called root. If it's point to no, that means there's nothing. It's an empty tree. So here we can see we have our A. A have two children, B, C. So you have his 2 pointers. B, C also have 2 children. To the left subtree, to the right subtree, D and E. And E is a leaf, so we end there. And also D have only 1 child, so it's pointing to G. So we said that a leaf is a node in a tree with no children, as we defined earlier. And also we are going to use the concept that let U and V be 2 nodes in a binary tree. So U is called the parent of V. If there's a branch from U to V, then V becomes the child. Now, a path from a node X to the node Y is a sequence of nodes X, 0, 1, all the way to N, such that S equal to X0, Xn, which also equal to Y. And Xi minus 1, which is the previous node, is the parent of Xi. Always we know the parent comes first before the children. Parents always at the top, children at the bottom. So the node again, Xi minus 1, which is previous, will be the parent of Sy. For all I from 1 to N. N can be any size. So next, the length of a path will be the number of branches on that path. When we say branches, more or less going from one level to another, where we branch on the levels. And also a level of a node will be the number of branches on the path from the root to the node, as we said earlier. Again, we start from level 0, which is the root, all the way down, depends on the size of the tree, to the level. Let's say if we have 3 levels, then we start from 0 of the root all the way to the 3rd level, which would be all leaves. Always the last level, all the nodes are leaves. So the height of a binary tree again is the number of nodes on the longest path from the root to the leaf. So we start with the method. Now we can say the height is very straightforward because we say the height of a tree will be the number of levels plus 1. So here we are using the concept of recursion, which is more easy to implement. Again, the lowest case would be if the tree is empty, then the height is 0. So we said that if P equal to null, P in our diagram will be the root. So for example, we have a special pointer to the root. We call it root. And so in our code, we call it P. So if P is equal to null, point to null, then there's nothing. We return 0. There's nothing. Else, as we said, the levels start from 0. So we are going to say 1 plus, we call the height of the P dot left link, which is the left subtree, and also the height P dot the right link, which is the right subtree. So the longest will be the value we get. That's why we are using mass. And mass, again, we know is a method in a math class. And so again, this is a recursion. We are calling the height, which is the same, the name of the method, to give us the P section, and also to give to give us the left subtree section, and also the right subtree. This is the pointer moving from each level. And math.mass, because we want the height, the value. So how many levels it goes through, the maximum one will return, then we had 1 to it. And that will be the height of the tree. Okay, so next we have a method called copy tree. And the method name again is copy tree. it will return since there we are copying the tray, so we're going to return the data type of the content of the tray, which will be nodes. So it's called a binary tray node. So we're going to return binary tray node to make a copy of it. And the argument will be the copy other tray root, we'll make a copy. Now here we declare a temp variable, which is also the type is binary tray node. And we are saying that if the other tray root is equal to null, because we are copying item from one, we make a copy of it, cron tray to cron it. So if there's nothing to cron, then we assign null to temp. What will happen is that when we cron it, we put a copy in the temp, then we return the temp. So first we check if the tray that we want to copy its root is point to null. If it's point to null, that means it doesn't have any, it's an empty tray. So we return null. Else, we assign the temp, which is the binary tray node type. And then we have the other tray node dot cron. So we call the cron method to cron it. We will have this method in our code. So, and this method will make a copy of other tray root, and we will assign it to a temp folder. Now we also need what? The left subtree and also the right subtree. So we use the copy tray. Again, other tray root dot left link. Same thing, copy tray, other tray root dot right link. And they will be assigned to the temp left link and the right link. Then we'll return the temp. So this will make a copy of the tray. So next, we go through the concept of binary tray transversal. This is one of the important concepts here. We know we have in stack, if I want to go through items in stack, the whole concept is last in, first out. If I want to reach the last item, I have to pop everything, then take the last. In queue, first in, first out. If I want to take anything, I have to start from the front. Binary tray, we have different way of transversing through the tray structure. And the most common way is using the in order, pre-order, and also post-order. We also have the level order, which we will explain. So with binary tray, these are the possible operations we can do. And more than this, and we'll see our binary tray class in a few slides later. So here we say the item can be inserted into a binary tray. We can delete an item from a binary tree, or we can search an item if it's inside a binary tree. So this is required by a binary tree transverse. If I want to insert an item, I have to go through the binary tree or delete, or especially to search for an item in the binary tree, I have to go through all the items. If the item is last or we don't have it, then we need to go through all the items in the tree. So again, those are the three main methods for now: in order transversal, pre-order transversal, and post-order. Again, the name depends on when we visit the root. So for example, in order transversal means I will visit the left subtree first, then I'll go to the root, then I'll visit the right subtree. That's why it's called in order. It's between the left and right and it's inside. Now, pre-order means pre, which means I have to go through the root first, pre, before I go through the left subtree and the right subtree. The post-order means post, which means I'll go through the root last. I'll go through first, go through the left subtree, then the right subtree, then the last will be the root subtree. That's post. Now we say the pre means what? pre, so we go through the root first before left and right. Again, in order means the root is within the left and right, so we go through the left first. Always when we have option for left and right subtree, we always go through the left subtree first before the right subtree. So let's go through the steps. So the binary tree is transversed as following for the in order transversal. We transverse left subtree first, go through left subtree. Then we visit the node. Visit node means again we go to the root. Then we transverse the right subtree. So this is the code for in order. Again, the method name is in order. So here we say that, okay, if the P, the special pointer that point to the root node, if it's not equal to null, that means we have some node in our tree. The tree is not empty. So again, this is in order. So first, we have to visit the P.left link. So we have to go through the left subtree. You can see that we are doing recursion here again in order because we may have more than one node in the left subtree. So we visit the left subtree, then we go to the root. Normally here we write system.out.print P, the root. Then we go, the root is only one. So we don't need to use the recursion to call the function. Then we go through the right. Again, the right subtree can have more than one node. So we say in order P.right link or R link. So again, same concept as we see in the theory. Go through the left subtree first. No matter how many nodes you have in the left subtree, you have to go through all of them. Then you visit the root, then you go through the right subtree. Now the pre-order, we said we visit is pre, so we go through the node first. So we visit the root, then we transverse to left subtree, then transverse to right subtree. So we can see here, we are saying that if P not equal to null, then go through, again, the root is only one node. So we use system.out.print, then go through the root. Then after that, we go through the left link and then the right link. And then the post order, as we said, we go through its post, so the root will be last. But still, we go through the left first, then the right then. So this is the code. If P not equal to null, then go through the left link, go through the right link, then the root. So this is our implementation of a binary trace. Again, in some textbook may use different names, but the whole concept are the same. So this will be our ADT file for binary tree class. So we don't have no instant variables. The methods we have will be the cron to make a copy of the tree. We can also check if the tree is empty. Now, since this is a dynamic implementation using the nodes, we don't need to check if it's full. So we just check if it's empty. Then we have the method to transverse in order. We also have the method to transverse pre-order, and we have the method to transverse post-order. Then next, we have the method to check the height of the tree. We also have a method to count the number of nodes we have in the tree. Also, we can also count the number of leaves we have in the tree method. We can also destroy the tree. We can search an item in the tree. Also, we can insert an item in the tree. And also, we can delete the node in the tree. So these are the possible methods, or I would say the operations we can do in binary trees. Now, this is our main implementation now, which are almost the same methods, but this time we have our instant variable. Here, the root is a binary tree node. The type is T, so generic type. So we have the binary tree constructor. We have the cron to cron. We can check if it's empty. We can do the in-order transversal method. We have it. Pre-order transversal also, then the post-order transversal. Then we have the method to find the tree height and also tree node count. We also have the method to destroy the trees, search an item in the tree, or insert an item into the tree, or delete an item from the tree. Now we have our transversal methods in order, pre-order, and post-order. We can also find the height of the tree, and the node count. This will be for, again, the binary tree node, and then the leaves count, and also copy tree. So let's implement some of the methods. So first we start with the cron. To cron, first we check if the binary tree copy equal to null. We assign null to it. Then we call our exception try. And we have binary tree super.cron. If we don't have no cron, we catch it using a cron not support exception. It cannot work. Other than that, we return null. Now we say that, okay, if the root is not equal to null, then let's make the copy tree root to copy.root. Then we return the copy. So again, that will be the conclusion of our lectures on trees. Again, we focus mostly on the theory aspect, and we are going to do the implementation first as a classwork and also as assignment for the class. So again, thank you very much for your time.